Hi, everybody. Welcome to lesson one on the properties of waves. So what I have here is just a YouTube video, and this YouTube video shows a really interesting way of generating electricity, and it's harnessing the energy stored in an ocean wave. So these big cylinders basically move up and down with the ocean, with the waves, right? And as they move up and down, they actually move a piston that consists of a coil of wire and a magnetic field, just like how you saw with the generator simulation in the past week's work, and changes the amount of field in that coil to generate electricity. So works in the exact same way as the generator that we saw before. The only difference is that this is harnessing the energy of the ocean waves rather than like a hand turning a crank. So we're going to focus on the waves, not the electromagnetism part. So let's go ahead and play this thing. Okay, so here you see these things moving up and down with the waves, right? They're taking that energy. Now, this is what I'm really interested in showing you. If we focus on one of these drums, let's say this one right here. Ready? Let's watch the motion. I'm gonna play it. You see that it goes up and then it goes down, right? So that drum is moving up and down. It's a drum, or we can call it a buoy. It is moving up and down with the water. It's not moving itself like left to right or front to back. It's just going up and down. But if I go backwards quickly in the video, I'm going to play until I reach that point again, you'll notice the wave itself is moving in the perpendicular direction. It's moving these buoys in that direction towards the back of this thing. So if I wanted to draw an arrow representing the direction of motion of the wave itself, it's this way, right? So the wave moves from this point to this point, from front to back, but the particles in the wave, and I'm saying these buoys or drums are basically the particles, they move up and down. So the wave goes higher, 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 and it moves in that direction. And let me play this again. There we can see as the wave comes in here, they're raised up, and one at a time they get raised up, and we see that the energy is moving from the front to the back, while the individual objects just move up and down. So to show this even more clearly, I have a simulation here. In the simulation, I have a hand that's holding on to some sort of, it's like a string of beads, almost like a rope that has these little beads on it. This rope with the little beads is what we call a medium. A medium is the object that the wave exists in or moves through. So for the ocean power plant, the medium is the water itself, right? That's what is carrying the energy. In the simulation, it's the beaded rope that's going to carry the energy. So what I'm going to do right now is, let me hold on. Okay, so I'm going to have the hand create what's called an impulse or a pulse. It's going to go up and then move down. And there we see this wave section move from left to right. The pulse is basically a small section of wave that moves off with energy. So create that again, and then I'm going to pause it right about there. Here we see again that the objects themselves, right? This object is at the top. They're only moving in this direction, right? This one right here is moving up at this point in time, while this one is moving down, right? And then eventually this one is going to move up, and this one's moving up while this one's moving down. But the direction of the wave's motion is again very clearly this way, right? That's the speed, the direction of the velocity, I should say. So particles go up and down while the wave moves left to right, carrying the energy from the left side where the hand was towards the right side. Okay, that's what a wave does. It transmits energy without moving the particles themselves. This type of wave in particular is what's called a transverse wave. And a transverse wave is a wave where the particles move perpendicular to the direction of the velocity of the energy of the wave. So here the energy is moving to the right, but the particles are moving up and down. There is another type of wave, and in that type of wave, the particles actually vibrate left and right like this as the wave moves towards the right. Okay, so there's the very basics of what a pulse is and a wave, just a material that carries energy. Okay, so now if I wanted to, instead of making a pulse, I could create what's called a sine wave, right? We all know what a sine wave is. This motor is basically just going to go up and down, and it's going to cause this bead right here to oscillate up and down. As it does that, the wave is going to continue to move out. And so here we can see that, right? Here's my wave moving from left to right. If you follow the point here, let's say that point, the maximum point right here, let me use the pen, right? When it gets to right there, right at the top, that top point is what's called the crest of the wave. So if we follow the crest of the wave as it moves over, we can see it's actually moving at a constant speed through the medium itself, right? Constant speed. Down here, this lowest point, right there about, that point is called the trough. And we see that it follows right behind the crest, actually sandwiched between two crests, right? Oops, zoomed in, moving along. Okay, so this is now a sinusoidal waveform, right? I can pause this at any point. There we go. And when I pause it, I see that I have multiple waves here. And I can count, right? Here's one wave about. Here's a second wave. Here's a third wave. And here's a fourth wave. Oh, no, not a fourth, excuse me. It's about a half of a wave. So I can say there are 1, 2, 3, 3.5 waves on my screen right now. Now, the full thing is a wave, but from one crest to one crest, right, or one trough to one trough is what we call one lambda or one wavelength. A lambda is the letter that we use, the Greek letter used to represent a wavelength. Okay, so here's a wavelength, here's a wavelength. I can also say that from this line to this line is a wavelength, right? There to there, there to there, so on and so forth. There are a bunch of them. And I have several crests here, here, and here, and troughs here, here, and here. Cool. Okay, so here I have another simulation through the PhET website. This one is just like the others linked in the first assignment for this week. This here is the frequency generator. So this little rod will go up and down, creating the waveform that will move to the right while the particles oscillate up and down. I've been able to set some things here. I've set the amplitude and the frequency. Now notice there's no wave here yet, but I still have those values. The reason why I have those values without actually having a wave is because the frequency generator hasn't been turned on yet. Now that may seem either obvious or like a silly point to make, but it's actually a very important point to make because what it tells us is that the frequency is determined only by the generator itself. I can change its frequency and this will move at a different rate, which will give me a different frequency in the wave. The amplitude also is set, which means that that's also going to be determined by the generator itself. So if I play this thing, I will have a wave that has an amplitude of 1 and a frequency of 1, all because the generator has nothing to do with the medium. So I can go ahead and do that. Right? Let me play it. So there we go. I have my wave being formed, right? Oscillating up and down, moving from left to right. So amplitude, frequency determined only by the source here. Now, the medium, which is this beaded rope here, that medium can be changed, and I can change that medium by altering the tension within the medium. So if I go ahead and I decrease my tension to low here, let's see what happens. Play it. All right, so I've had some sort of a change. The wavelength of my wave has decreased, right? It's gotten much shorter in wavelength, but notice the amplitude stayed the same. It's still going to this dashed line. The frequency still stays the same because this goes up and down. What that means is if the frequency stayed the same and the wavelength changed, the speed of the wave must have changed. I can also change my tension to be high and run this thing. There we have an increase in wavelength. I've again changed the speed in the wave as the frequency stays constant. And the equation that you see in one of those, actually we'll work on a sample problem in just a moment. What I'm going to do now is I'm going to change my tension to low. Oh no, let me go right in the middle there. All right. And I'm going to open up a timer. What I'm going to do is I'm going to count the time for this to go up and down twice. All right, so ready? Start. Oh, I lost track there. Hold on. Okay. 1, 2. Okay. Oh, what did I just do? Damn it. Okay, one more try. Okay, I'm going to play this thing. I'm going to reset. I'm going to start when it's at the top. Start. Stop. Okay, so I got 1.92 seconds. Let's write that down. 1.92 seconds. That was the time for two waves to pass by, right? I had to go from crest to crest to crest. Crest, trough, crest, crest, trough, crest. That's 2, which means that the frequency is going to be 2 over that value, right? Or approximately, we'll say 0.5, right? Oh no, 1 actually, isn't it? It's even easier. So approximately 1. Well, it should be exactly 1, right? Because that's what we set it to. So that's perfect. It matches up exactly with our expectations. Now, let's see what our wavelength is. Well, I can count from a crest to a crest, right? And let me go ahead and move this ruler so that it's more convenient for us to use. So we're at about 1, 2, 3, 4, right? So that's going to be about 3.8 centimeters. So I can say that my lambda, the wavelength here, is about 3.8 centimeters. Well, if I wanted to find my velocity, that velocity is equal to the frequency times the wavelength. Frequency times the wavelength. That's going to be 1 hertz times 3.8 centimeters, or 3.8 centimeters. Remember, hertz is inverse seconds, so centimeters per second. There we go. We managed to solve for the velocity of this wave.